All right, welcome back. We're just going to work through some examples of L'Hopital's rule. So in these three examples, I'm going to do them all at the same time. I'm going to say, we saw how L'Hopital's rule kind of works before at the end of the last video. I want you to pause the video, give these a shot, resume the video when you're ready to see the solutions. And here you go. The first one ended up resulting in tangent. And so then if you look at the right side of pi over 2 for tangent, you go to minus infinity. And then the second one, you have to do L'Hopital's rule 3 times. I didn't show that work just because I kind of do it in my head. But you get infinity over infinity for the indeterminate form each time. And so then you end up with something as e to the u over 6 at the end, which you can evaluate and just get infinity. And the last one, the idea there was you had to figure out what the quotient was, right? So you just had to learn to rewrite it into something that had a quotient, and when you did that, it was sine of pi x, or pi over x, all over 1 over x. And then L'Hopital's rule gives you something that evaluates nicely to pi, okay? So those are all more quote-unquote standard type exercises. The next batch get a little bit more complicated. Okay, we have a quotient of things, and so, well, L'Hopital's rule only applies if you have one fraction, right? So what do you have to do? You have to, well, get a fraction. Yeah. So in each of these, what do we do? Okay, the first one might be as simple as just finding the common denominator. So limit as x approaches 1, and then the denominator is going to be quantity x minus 1 times natural log of x. And when I, add the missing pieces into the numerator, I get x ln x minus x minus or plus 1, right? And then now, if I think about this and look at this, right? Substituting in 1, this would go to 0, and then 1 minus 1 gives me 0 in the numerator. Denominator would be 0. Okay, so not great, right? So then now I have enough ammunition to do L'Hopital's rule. And then I'm going to tell you that I calculated the limits in advance, and we end up with natural log of x in the numerator, and the denominator can be x minus 1 over x plus ln x. You can verify that on your own. Okay, and again, once we do the calculation, we get 0 in the numerator, 0 in the denominator, and so then I have to do L'Hopital's rule again. So equals by L'Hopital's limit as x approaches 1, and then I get in the numerator x to the minus 1, and then the denominator x to the minus 2 plus x to the minus 1, which this time gives me 1/2. Okay, so one strategy, if you're given a difference of things that is a quotient already, find the denominator, or find the common denominator. Okay, next one, this is a little weird, okay, and that's okay, we can work with weird. So limit as x goes to infinity, I'm going to factor out an x, and then I'd have e to the 1 over x minus 1. Okay. Oh, and this is just like the sine thing, right? I can write this instead as limit as x approaches infinity of e to the 1 over x minus 1 all over 1 over x. Okay. And if you want to, I'm going to suggest you could do something like y is equal to 1 over x. And then in this case, if you do this, you have the limit as y going to 0 from the right, if you want to, if you don't want to. But either way, this form allows you to do L'Hopital's rule, and I'm just going to say after some simplification and work, you end up with something that gives you 1 as your answer. Okay, I'll let you fill in the dots there. I just wanted to kind of get you started, and I have full confidence you can fill in the dots. Okay, next set of examples are also a little weird. So, are these indeed indeterminate? Well, let's see. So here, if we did this, we'd have 0 to the infinitieth power, right? Well, if we naively plug that in, didn't we say that that wasn't that wasn't indeterminate. Okay, so that's not indeterminate yet, right? But I still don't know how to calculate it cleanly. So even though I don't know how to calculate it cleanly, right, this isn't indeterminate, so I can't use L'Hopital's rule. But I think at least if we take it on faith, like if this is the indeterminate form, there's only the answer of 0 that we can get, right? We can only get 0, okay? So we're going to leave that one there, right? That was thrown in just to kind of throw things off for you. The next one is also a little interesting. So 1 plus a over x raised to the bx power, okay? This one I like throwing in because it's a limit that looks familiar but weird. Okay, if we rearrange this be limit as x approaches infinity, and then I'm actually going to put this inside, this limit inside, and do 1 plus a over x all to the x, and then raise this all to the b, right? With continuity, and I'm going to guarantee you that we're going to get continuity out of this eventually that we can, retrospectively apply. We have something like this going on. Okay. Now this, if you remember, e to the, or just e, the number e, that was defined as limit as x goes to infinity of 1 plus 1 over x all raised to the x. So this looks very, very similar, except we have the a in there. What's that a going to do? Actually, this, you can verify this, but this is going to be e to the a, okay, inside, and then all raised to the b. So our final answer is e to the ab. Now, going from the limit to e to the a, you might have to take on faith, okay? But we can go through and verify that if we so choose. Okay, so don't think you have to necessarily do anything special with either of these first two cases if you're given, something that is expressed in exponential format. Okay, so my point is dig deeper before you try what we're going to have to do with this next one. Okay, with this next one, it looks a little bit more complicated. If we look at this and again naively apply the limit, so like substitute in, I would get 1, and then cosine at 0 would give me infinity, okay? And as I compare that to what our indeterminate forms were, oh my gosh, I'm losing my spot, okay, so 1 to infinity, I forgot to list it here, 1 to infinity is another indeterminate form, okay? So we need to try to apply L'Hopital's rule to the best that we can. Oops. Okay, I will find my spot. Okay, so now the question is, what do we do? Okay, it would be nice if we could not have cotangent of x in the exponent. And so what we're going to do is kind of sidestep here a minute and call this whole thing, the whole expression inside the logarithm y. So I'm going to call that y is equal to 4 to x plus 1 to the cotangent of x, and I'm going to natural log it. Why do I natural log? Well, because then the exponent comes down in front. Oh, look at that thing. Oops, 4x plus 1. Okay, and then it would be really nice if I could make this into a quotient, right? So then natural log of y is equal to natural log of 4x plus 1, and then, oh, okay, if I do the reciprocal of tangent, cotangent, that's tangent, right? So I could do that. And then now, resolving for y, I could do y is equal to e, I'm going to come down here and do this as e to the natural log of 4x plus 1 over tangent of x. And now I can come back over here, so bring that back over, and do, this is the limit as x goes to 0 from the right of e to the natural log of 4x plus 1 over tangent of x. Okay, and now remember we had a limit rule about continuous functions, and you can move the limit inside continuous functions, and that's exactly what I'm going to do. So I'm going to say this is e, and then to the limit as x goes to 0 from the right of natural log of 4x plus 1 over tangent of x, and then it is just like any other L'Hopital's problems. So I need to verify indeterminate form. Okay, if I do so, I would get 0 over 0. Okay, good. And then I can do by L'Hopital's rule, I would get e to the limit as x goes to 0 from the right. And then differentiating all this, I would get, let's see, I'd get in the numerator, I'd have 4 over 4x plus 1, and derivative here is secant squared of x. Okay, and now this, if I substitute that in, let's see, that'd be 4 over 1 and then over 1, so it's really just e to the 4 for my final answer. All right, so point being, with these last three, right, you could try just looking at it and try the naive approach. That always is a good first step. If you get something that results in an indeterminate form, right, then you might have to kind of sidestep a little bit and rearrange it using logarithms into something that is fraction form, to which you can apply L'Hopital's rule. Okay, so this video had many examples in how to work with L'Hopital's rule, and you will see more coming up. Have fun.